Hi, Dr. Lyons here, of course. I'm going to work some example problems on diffusion, specifically transient diffusion. And the first problem is as follows. A bar of FCC steel, which is an iron carbon alloy, is to be carburized using methane gas at 950 degrees C. Describe the primary mechanism of diffusion that occur in this process. So the primary mechanism of diffusion that occur in this process is interstitial diffusion. Interstitial diffusion occurs. And physically what happens is the methane gas decomposes. The methane gas decomposes, and the free carbon atoms diffuse through the interstitial sites in the FCC iron crystal lattice. Interstitial diffusion occurs. The methane gas decomposes and the free carbon atoms diffuse through the interstitial sites in the FCC iron crystal lattice. Question 2 is stated as, originally the alloy has a uniform carbon concentration of 0.25% carbon. If the concentration of the carbon at the surface is suddenly brought to and maintained at 1.2 weight% carbon, how long will it take to achieve a carbon content of 0.8 weight% carbon at a position of 5 millimeters below the surface? So we're looking for time because the question asks, how long will it take? Because we're looking at a transient diffusion mechanism or process, we are going to use the transient diffusion model. Transient diffusion model is in the Callister textbook that we're using in our class as equation 5.5 on page 127. Excuse me. And I'll write down the model. It is Cx minus C0 over Cs minus C0 equals 1 minus error function of the quantity x over 2 times the square root of dt. So what are we given in the problem statement? What are the knowns? We are given the following. We are given the desired concentration at a position x, Cx, is 0.8 weight% carbon. We're given the original composition of carbon in the alloy, or concentration of the carbon in the alloy, which is 0.25 weight% carbon. We're given the concentration at the surface of the piece of iron at 1.2 weight% carbon. The position that we're dealing with is half a millimeter into the surface. That's 0.5 times 10 to the minus 3 meters. And we're given that the temperature that this occurs at is 950 degrees C, which is 1,223 Kelvin. We're asked to find time t. So we're asked to find t. So we've got the three compositions or three concentrations of carbon. We've got x, and we need d to find t. That will reduce it down to just one equation with one unknown. So along the way, we are going to need the value of the diffusivity, and we will be using equation 5.8, which is D is equal to D0 times E to the minus QD over RT. And we'll look up in table 5.2 to find that the activation energy for diffusion, QD, is 148 kilojoules per mole. And the diffusion couple constant D0 is 2.3 times 10 to the minus 5 meters squared per second. So if I know T and R and Q and D0, I can find D. And that gives me everything I'm going to need to know to find T time. So let's start with the solution now. So the first thing I want to do is find the value of the error function with the given composition. So I'm going to be looking for ERF of x over 2 root dt. And if I just rearrange the equation 5.5, I see that is 1 minus Cx minus C0 over Cs minus C0, which is 1 minus 0.8 minus 0.25 over 1.2 minus 0.25. Which is equal to 0.4210. So that is the value of ERF. Where Z is x over 2 root dt. So I need to now find Z. Because I have ERF of Z, I need to find Z. What we're going to do that is we are going to interpolate in the error function table, which in our textbook is table 5.1. Okay, and here is the error function table. You can see that it is a table of values of Z and the error function of Z. And I know that I'm given, or I just solved, I guess, in this problem that ERF of Z is 0.42. So I need to find where in this table 0.42 falls. And so it's not there exactly, but 0.4210 is between 0.37 and 0.428. So I'm going to be interpolating between those two values of ERF Z to find the value of Z corresponding. This is a linear interpolation, which is okay for the purpose of this class, even though ERF function is not linear. Okay, so I'm going to copy these values down of 0.37 and 0.42 and 0.35 and 0.40 and make a little table on my own piece of paper here. I have values of Z, and I have values of ERF of Z. And the thing that I'm looking for is this value of Z at 0.4210 ERF of Z. And that ERF of Z is between 0.3794 and 0.4284. The Z value corresponding to the first value of ERF of Z is 0.35. And the Z value for the other known value of ERF is 0.40. This is the calculated value of ERF of Z, and I'm looking to find that Z. There's a couple of different ways you can do interpolation. The easiest way that I've found is to say that this number in the middle is to that number at the bottom, as this number at the top is to that number at the bottom. And the ratio of those two distances is the same as the ratio between these two distances. So write that down. That means that Z minus 0.4, 0.40, is to 0.35 minus 0.40 as ERF of Z, 0.4210, is to the bottom 0.4284, or is the difference between those two numbers divided by the difference between the two values from which we are interpolating, 0.3794 minus 0.4284. And we do some math, and we find that Z is 0.3925. Recall that Z is x over 2 times the square root of dt. And that in this problem is equal to 0.3925. Well, from the Z, what we're looking for is to find the time t, which if we rearrange that equation, or if we solve for t, we're looking at t equals x squared over 4 z squared d. Oh, I need d still, because I've got z of 0.395 and I've got x, which is half a millimeter. I still need that d. Okay, maybe I wish I'd done that a little earlier, but it's never too late to get the number we need. We need d. The equation for d is d equals d0 times e to the minus q sub d over rt. And we were given, or we looked up values of q and d0. As I mentioned before, we wrote those down in the problem statement. So we can plug those in here. So I've got d is 2.3 times 10 to the minus 5 meters squared per second. And that is times E. I'm going to write a big bracket here. Minus QD was 148 times 10 to the third kilojoules per mole. And R, the gas constant, is 8.314. I'm sorry, I think I got the D. I got the units on that wrong. It's 148 kilojoules, or 148 times 10 to the 3 joules. Make that correction. A gas constant is 8.314 joules per mole degree K, and the temperature was 1223 degree K. Okay. So again, I do some math with my calculator, and I get a value of D of 1.103 times 10 to the minus 11 meters squared per second. So I substitute that into my equation for T, which was x squared over 4 z squared d. So my x was, I believe, 0.5 times 10 to the minus 3 meters, quantity squared. Divide that by 4 times z, which was 0.3925 squared. And the diffusivity, which is, we just calculated, was 1.103 times 10 to the minus 11 meters squared per second. Okay, and just looking at my units here, make sure everything's going to work out. I've got the meter squared there, and I've got the meter squared there. Seconds in the denominator of the denominator, so the units of this are going to be seconds, which is good because time is measured in seconds. Do some more math with my calculator, and I get a time of 36781 seconds. 36,000 seconds. That is equal to 10.2 hours. So I have answered the second problem, which was to find the time, or how long it took to achieve a carbon content of 0.8 weight percent at a position of 0.5 millimeters below the surface. Okay, now let's do the third problem, which says determine the time necessary to get the same result at 1 millimeter below the surface. Well, first you might think we have to do this entire problem again, but we've actually done a lot of the calculations that we need already. And the key here is we are trying to get the same result just at a different distance. So that's cool. So what I'm trying to do is to find a new time, T2, for a CX equals 0.25 weight percent carbon at X equals 1 millimeter, 1.0 millimeter. I'm saved from some time, at least, by the fact that the problem says get the same result. So nothing's changed in terms of the diffusivity or anything. So therefore, we actually have the same diffusivity, and we have the same Z, the same result, the same value of Z, just at a different position. So by Z2 is equal to the Z from the previous problem. And Z2 is x2 over 2 times the square root of dt2, and that's equal to x1 over 2 times the square root of dt1. Since the d's are the same, those can cancel out, and the 2's can cancel out. So looking at the ratio of x2 over the square root of t1, I'm sorry, t2, x2 over root t2 equal to x1 over root t1. Solve for t2, it's equal to t1 times the ratio of x2 over x1 squared. T1 was 10.2 hours. X2 is 1 millimeter. X1 was 0.5 millimeter. That's squared. So I get an answer of 40.8 hours. So it takes about, in this particular problem, it takes about 4 times longer for the carbon to reach the high level of 0.25% at just twice the distance under the surface. So, thank you for watching.